Good morning, everybody, and welcome to EGU25, the biggest General Assembly of Geosciences in Europe and the second biggest one in the world, with over 20,000 participants attending both online and on-site here in Vienna. So today, our fourth press conference is titled Power Trips Building for the Future with Resilient Climate Technologies, where our panel will explore innovative technologies designed to bolster energy infrastructure resilience, ensuring that power systems can withstand the unpredictable impacts of climate change. From improving grid stability to integrating renewable energy solutions, these advancements play a pivotal role in ensuring a sustainable and secure energy future. So today we have Hiba Mary from the University of Debrecen in Hungary. We also have Sanja Duvniak-Zarkovic from Uppsala University. And last but not least, we have Stefania Ursika from the GFZ Helmut Center from Potsdam, Germany. Thank you.
All right, I start with these headlines. This is why I'm talking to you today, because there's a direct link between climate change and geomorphic events turning into disasters. And these headlines will just proliferate unless we outpace them. For that, we need rapid perception, rapid detection, and location, because we can't really predict them at this point in time. And this rapid perception is critical for several reasons. For example, it helps us quantify the mechanistic links between drivers, in our case climate, and the geomorphic processes. It helps us understand comprehensively landscape evolution, rates of change, of instabilities in the landscape, not to speak about early warning and rapid and targeted intervention that can reduce uncertainty, can reduce panic, climate trauma, and all kinds of losses. And we can personalize climate change. We can bring it to local, immediate, so that people have relatable cause and effect and perhaps act. So I'm Stefania Ursika from GFZ Potsdam, and today I'm going to ask whether we can be inspired from biology. Can animal behavior sharpen our ability to locate geomorphic events? Well, an elegant solution is tapping into seismic data. So we have a global network of stations that listen, that record tremors on subsurface and surface. And technically, we could detect and locate using this data geomorphic events too. So we agree that earthquakes and geomorphic events can fracture reality in the same way, but they are not equally easy to detect and locate seismically. And that's because look at the signals. So the earthquake signals have this crisp wavefront. They are kind of coherent, predictable. And if you look at a landslide signal, we have this emergent, smeared onset that is hard to detect and correlate. What we did is we repurposed tools from subsurface to the surface, but we struggle because we left a relatively uniform and quiet underground to a messy, noisy, chaotic surface. So this is our challenge in location. What we see here is one of the biggest landslides in Canadian history and actually in global history in Mount Steele 2007. In the time it takes to counter 180 million cubic meters of rock and ice, plunged 2,000 meters and traversed 6 kilometers, it was on a glacier, but imagine if it's a town full of people. And what I did is I took the relevant data from 9 seismic stations nearby, marked with red on the map, and I used 2 standard techniques to try to locate. These are marked with yellow on the map. In both cases, as you can see, there's a significant mislocation relative to the true source. With purple markers, you can see the top and the toe of the landslide. So what is our solution? Is to actually draw inspiration from biological systems. These systems have had millions of years to try and fail and try and fail and find the right strategies to some of the problems that we also face, like how to search and how to find in complex landscapes. For this, we combine biomimicry with geophysics, and we create this algorithmic workflow that is fully dynamic and adaptive. And basically, we go from an event like Mount Steele landslide, but we don't know exactly when and where it happened, to a more defined time and location. In this talk, I will focus on presenting you a picker for time and a biolocator. These are our innovations. So basically, when we hear about an event, whether it is reported or detected, our algorithm automatically knows what stations to query data from and creates this dynamic and directionally adjusted search area. You can see it with shaded light on the map. And within this area, we are going to try to find the location later. And now, one of the key innovations is this picker. The idea is to pick the onset time of a geomorphic event. We blend 5 distinct detectors. Each detector has a different role. It looks at a different perspective of the waveform. They can span from statistical models to more complex aspects. The idea is that we put together this information, and that can give us the first time we can identify the event on each data from each station. So here's one of the detectors, just to show you that we use some Bayesian statistics to find change points or breakpoints in our data. We make these posterior probabilities, and you can see with the yellow curve, these probabilities, the data is with blue, and the purple line shows the ground truth. That's the time we want to detect. The yellow curve shows that the significant spike that deviates from the background closely aligns to the ground truth. Now, if we put all 5, because this is just one of the detectors, into a composite picker, and that's our method with blue, and you see the other method with red, that's the classic one, you see a performance gap. Our is more sensitive, it's earlier and closer to the ground truth. And this is systematic. What you see, it's a distribution of the time differences between what we want to detect and what we detect. And we want ideally to be 0. You see that our model is brackets closely to 0, while the classic one wobbles more. It's more erratic. This propagates into the velocity field. Velocities are crucial in location. Because we have good times, we can create this model of velocity instead of assuming one that's unrealistic. And here's the second key innovation, where we basically combine geophysics that give us this rough, coarse ballpark, which is still too large, and then we put the bio-inspired layer that is able to refine to the near true location. And here is an example of how this biolayer functions. So we have agents that mimic animal behavior. Each animal behavior is encoded mathematically. Here's an example of the equation for the falcon. It basically models how the falcon dives and spirals inwards as it dives. We encoded more than 10 such animal behaviors that have different strategies. So from vast exploration of whales to the memory of elephants, to communications of the fireflies, getting out of blind spots or stuck places through lemurs or echolocating bats, and to refinement in the end of the hummingbirds. And they all evolve and become more and more specialized. So do you remember the ballpark from the geophysics? And now we drop these agents in this ballpark, and they start to move around the stations with red. With white dashed line, you see the path of one agent. At each step, it will simulate a synthetic waveform, so how a signal should look like if the landslide had originated in that point. And we compare it to the original waveform with blue. So synthetic with yellow, real data with blue, and we compare them and compute the difference. That's a composite misfit. The lower the difference, the higher the fitness. Remember, we are in evolution. The fittest will always survive and near the true source. And here is the result of our biolocator method with blue marker. And you can see it relative to the true source with purple, and again, the standard techniques. The uncertainty is also very low. It would be an ellipse just around the pin. And here is the distribution for 30 events across the globe, of different events, from landslide to debris flows to pyroclastic surges. And with purple line, you see the standard technique that we use in both picking time and locating. You see this broader distribution with a wider tail. With green line, you see the geophysics part with the hybrid picker. And with the blue is the geophysics part plus bio. So basically, you can isolate in the blue line just the bio component. It's pretty evident that already in the green curve, we are shifting within 70 kilometer of deviation, because on the x-axis, we have the location deviation in kilometer relative to the true source. And we remove the extreme cases of over 200 kilometer deviation. What we see with the biolocation is a peak density of 4 kilometer, and we have basically an order of magnitude improvement. So bio is not just cool, it brings real improvement. So how fast is this? Well, Jesse Owens' record is a good description. And I will conclude my race just as fast. And if you have questions, because I'm out of time a bit. Thank you.
Now we're going to give the floor to Sanya.
Perfect. Thanks a lot. Thanks for the invite. I'm super thrilled to be here and to share the stage with Stefania and Heba. It is my first time at EGU, and I'm mesmerized by the scale of the event, so really good job. Anyhow, my name is Sanya, and I'm a postdoctoral researcher at Uppsala University in Sweden, but I'm also affiliated with CLIMES, which is a Swedish Center for Impact of Climate Extremes. And it is an amazing platform that brings researchers with different backgrounds to address challenges with climate extremes. And my background comes from power systems and electrical engineering. And I'm going to tell you something about my research. So my research has been mostly focused on security of electricity supply, which is a fundamental requirement for modern societies. So it's the ability of power systems to provide users with electricity in a reliable way, with good quality and at affordable prices. And I have tried to identify what are the dimensions that constitute security of supply, and I have been mostly focusing on reliability and resilience. Now, in simple words, reliability is the probability that the electric power system can perform a required function under a given condition for a given time interval, while the resilience looks more into how to adapt to different extraordinary and disruptive events, how to learn from the past, and how to anticipate future events. So in simple terms, reliability is like a binary. Is it work or does not work? Is it a system available or not? And resilience gives you this kind of time continued. How the infrastructure behave, how the system failed, how much time did it need to recover, and so on. And recent events in Spain and Portugal just say how important is electricity of supply. And we take it for granted. And we want it 100% of the time, right? So if I tell you, okay, our security of supply is 99% of the, what do you think? Is it good or bad? It sounds good, but in reality, it means that 87.6 hours people will experience outage. That's what it means during the 1 year. So it's almost 4 days. It can be 4 consecutive days, but it can also be spread out throughout the year. And it's on average. So many European countries now are aiming for 99.95%, which is bit less than 5 hours. So there is a high requirement for good quality and good reliability of supply. So since I come from Sweden, let's see what's the situation in Sweden. How is it security of supply? So this is the figure that shows the security throughout the years, I think up till 2019. And most of the time it's quite good. It goes above this threshold, 99.95%. But these dips that are happening, it mostly related to big weather events and big storms that had hit Sweden during this period of time. So the biggest one was Gudrun in 2005. and it had devastating effects. Now, it doesn't seem that bad, 99.8%, but I need to say it's average per region and average per number of customers. So some parts can be affected more, some parts can be affected less. When you average it, you get this number, around 18 hours per year, right? And if we look at the power system globally, we can divide into 3 levels. So transmission grid, highest voltage, then we have regional grid, and we have local distribution grid. And this figure relates mostly to the lowest part of the grid, so the local distribution grid and part regional grid there. So what I've tried to do in my research is actually to gather outage statistics in Sweden. Now, there are around 170 distribution system operators that need to report, they have obligatory to report the reliability statistics to Energy Market Inspectorate. But they had a very good initiative in the previous years because of these weather events that were happening. They were collecting and giving voluntarily statistics for research purposes, and unfortunately they have stopped doing that last year. So I managed to gather this. I got 2 extra years recently, but my analysis only can include this one here. And what we have found out that there are different causes that are causing outages, but we can see that weather is in the 3rd place right now. It's around 26% caused by weather-related events in Sweden. If we look at the number of affected customer, weather is coming on the 2nd place, so around 33% caused by weather-related events. And if we look at the customer interruption time, which is the time during the customer experience interruption, it was without electricity, it's number 1, around 58%. So it's kind of alarming in a sense it needs to be addressed. So that's why our research is looking into weather events related to power outages in Sweden. And my idea here is actually to use the real data and to get insights, to merge outage statistics and also meteorological data. So outage statistics, I've shown you what I've managed to gather during these years, but quite often people are not willing to share this. I mean, we're talking about security of a national grid, so that they're not always willing to give you the data. You need to be very persistent. And very often there are sensitive information with this outage data, so not everything can be displayed. And what I have found by analyzing this is that the location is not always easy to pinpoint, so where the outage actually happened. On the other hand, meteorological data, there is abundance of it. In Sweden, there is SMHI, or Swedish Meteorological and Hydrological Institute. They have gathered meteorological data for like, 80 years, since 1960s. But unfortunately, the format of this data is not always desirable. So right now, I'm working with very brilliant computer linguists that are helping me use natural language processing to extract data that I need, that are relevant, that I can use and compare with outage statistics. And once I have these databases, I can correlate them using different tools such as Power BI, etc. And the impact of this is, I think, very, very relevant in the sense that we can get insights how the system behaves, where are the vulnerabilities, where the reinforcement needs to be done. So we can make intelligent decisions how to improve our system and how to improve security of supply. And it can be also a baseline for the future scenarios. So how can we, for the future scenarios in the sense, how can we predict and how can we anticipate some events that haven't happened before, and how can we be better prepared for that? So thank you.
Thank you much. Thank you very much, Sania. And now we are going to move to our last speaker, Hiba.
Hello, everyone. It is my honor today to stand before you to share with you some results from my PhD dissertations. My topic, and this is a part from my topic and dissertation, speaking about the potential synergy between the integration of green concrete material and the nature-based carbon dioxide removal in residential building sector. Start first with a brief introduction. Increasing the population growth all over the world expected to reach to 9.7 billion by 2050, and this is resulted 3 billion people will live in housing by 2030, and this causes rapid urbanization and also increasing the number of residential building. Only in 2022, 90,000 housing unit per day globally, and this has resulted very huge consumption for construction material and depletion of natural resources. Only construction material reached 26 billion ton per year, and causes energy use and maybe depletion of natural resources. And most of this construction material is mainly concrete material, which reached to 14 billion cubic meter in globally. And also, this is concrete material depended on one material most important, which is the cement, 4.1 billion ton in 2022. Here is the problem. Cement is the most contributor to CO2 emissions, 8% globally, and we should find new solution and a new strategy for how can you reduce this is material with this increasing of number of residential building. For that reason, we find for green concrete and nature-based solution as a sustainable solution. Here is my research focus on green concrete, which reduce cement, reduce CO2 emission and waste generation, and also reduce aggregate. How can green concrete reduce cement? Because it's dependent on its component for alternative material instead of reduce the cement, like fly ash concrete and also recycle aggregate concrete. On the other side, cement contribute with CO2 emission, so can reduce the CO2 emission based on cement production, and also reduces based on reducing the natural aggregate consumption. So there is a double effect for using this material. And recycle aggregate concrete connected strongly with waste generation, especially in construction demolition waste, which is dependent on the concrete derbies. So we can absorb the waste stream from concrete and reform this to new material, for using for new building. Reduce natural aggregate. This is connected with also construction and the demolition waste, which instead of natural porous aggregate as a concrete derbies. On the other side, we want to integrate it all as a sustainable strategy between using green material and using green system. Green system here depend on green roofs, which reducing cooling and heating can reduce energy, providing insulation for the building, and also make it a good environmental air quality inside, and also carbon dioxide sequestration. In the same regard, we find here green facade, which carbon dioxide sequestration and also reduce wall temperature and enhance biodiversity. Moving to the next slide. My topic here, my research in concern with Egyptian residential case study, which here faces challenges and opportunity. One of these challenges, which population growth expected to reach to 177.5 million by 2060, and based on that, there is a reform from the government reform strategy to increasing the urbanization and increasing the number of residential buildings to absorb faces these challenges. So increasing the number of residential reached to the maximum level in the last recent year. But the opportunity here, there is an Egyptian institution and Egyptian voices that there is a Green Building Council which support the green practices, and also there is integrated sustainable energy strategy support this practices and Egyptian Vision 2030. If we see here in this map, we find here is a consumption only for from 2020 to 2023 is reached from 42 million to 50 million. So it is very, very huge indicator for increasing the consumption of cement regarding increasing the urbanization in Egypt. This first case study, my research focus on two case studies. The selection of the case study come dependent on this is a common building typology in the next currently and in the future. This is a economic building. It is not green building because I focus to apply in something can be more impact in the future. This is an economic building. This one located in new cities named Al Burj Al Arab cities in Alexandria Governorate. And this is the location for the building. This is a real and existing building. Objective here aim to investigate the potential synergy of sustainable building. How can integrated green concrete material with nature-based solution as a sustainable strategy regarding green walls, green facade, green recycle aggregate concrete to reduce CO2 emission. Methods here depended on two stages. The first stage, design-based solution, which concerned with changing the design to be able to apply all of this strategy. The second, system dynamic-based framework. And here is the building after modified. This is the modified building one, after modified to be able to apply the green concrete. And here is the reduction for the cement by from 100 to 91.9%. And here also there is a result. Cement consumption here reached to 80.6%. And in some specific building parts, which was used in the recycled aggregate concrete, reached to 55.5%. On the other side, we able to also reduce natural aggregate and reduce CO2 emission, reduce natural aggregate by 23.7 and CO2 emission by 44.5%. This is the main result from the first stage. To continue for more enhancements, our result, and for more reduction, we apply it in the case study 2. Case study 2 located in another new cities in Egypt, like name New Cairo city. And also this building is economical building with the same feature and the same, almost the same size. Here we classify the concrete for 5 types. These 5 types make it 7 scenarios, and we try to quantify these scenarios and compare between us to select what is the most optimum scenario can reduce CO2 emission. We find finally here the reduction for the most optimum scenario based on causal loop diagram. When we applied the system dynamic, we first created the causal loop diagram based on a circular economy strategy and sustainable development together to find what is the most optimum variable can working on. Here is the causal loop diagram identifies the interrelationship between all these variables to be what is exactly processes will go on. Based on that, using Venzim software, we transfer to a stock and flow diagram to know what is exactly will happen in the construction process. This is diagram benefits, add more benefits for investigating what is exactly will happen for the consumption of cement before the construction processes start. Because after it started, there is a consumption and maybe waste increase if we change our mind. But here we can decide it before it starts. So we can know what is the exactly most type of concrete can be useful for reducing natural aggregate CO2 emission and also waste generation. After that, running the simulation, the diagram here shows that is the reduction in CO2 emission in the type for green concrete based on fly ash, which reduces cement from the production and also reduce waste generation. Here we find the reduction for natural aggregate and the reduction for also here is a natural aggregate based on fly ash and based on recycled aggregate concrete and the cement consumption for different concrete building type. After that, we make it our comparison to know what is the best one and select it and put it. This is as a clarifying for guideline for how can use the green concrete and the nature-based solution for residential building and contribution with SDGs. This is the final. This is considered as a guideline for policy maker to know what is the contribution between this and green concrete in the SDGs. It's contributed very strong with goal 12 and also goal 9 and goal 3 and so on. So this is a brief summary for my work, but there is second phase. It will be concerned with the operational stage regarding this residential building. So, thank you so much. I hope I can explain. Thank you.
Thank you so much for our wonderful panel. And now I'm going to open the floor for questions. So does anybody from our audience have any questions for our panelists?
Hi, a question about the locating of landslides and so on. I wonder if you could explain to me the context a bit more about why it's so important to get the precise locations and what difference that makes.
Yes, thanks for the question. I think it's really important. So in the context of accelerating climate change, we can expect accelerated geomorphic processes. And most of these processes will happen in areas that either we don't know when and where it happens, or they're populated. And then it's obvious that it will cause a lot of loss, not just material, but loss of life, for example. Now, knowing precisely, I'm not sure if I can actually have a slide back, but if you remember my Mount Steele example, so that was a huge landslide, 80 million cubic meter. If there's a town at the bottom of the mountain, and there you have to understand that the context is with mountains up to 4,000 meters. So something happens like a tragedy. May I have the mouse, please? And you need to dispatch helicopters with quick aid to that place, and you dispatch it to the wrong place. So here is the landslide, and you capture the seismic data and you don't locate it precisely, and you go into this valley. Then the helicopter has to, because it's in Alaskan area, to actually go back to the main town somewhere around the coast, and then go back, and that's a lot of effort and time lost that can be crucial, for example. And in general, for example, it can reduce misinformation. The credibility of data can build up trust. That can also bring justifications, but most importantly, the rapid intervention, that's what we need. And then when we have precise location and we know exactly where things happen, then we can, for example, have a better understanding in general of how landscape changes and where is vulnerable. And that can have implications even in places where you don't necessarily think directly, like, for example, insurance market stability, right? Or road construction or road maintenance and so on. I think this is not just we can go from bird's eye view, so comprehensive understanding from the landscape, to the actual local immediate impact. So precision, accuracy, and most importantly, as fast as possible is what we can do unless we learn how to predict these geomorphic events.
Maybe I also have a question for you.
Okay, thank you.
So first, just to make sure I understand correctly, so the location in this question, in this matter, is the final destination of the landslide rather than the source. But you would be able to extrapolate the path of the landslide from that information.
All right. So at this stage, what we can do is get as close as possible to either to the source, which in our case is the top of the landslide, and the toe. So maybe I can show again the slide. Our locator, it's exactly, so the location of our hybrid bio method is between the top and the toe, so somewhere in the middle. We want to get as close. There will be some uncertainty involved always. In our case, it's about 300 meters on average. That's already quite important if you get, let's say, within 5 to 10 kilometer, because what we had before is 40 to 50 kilometer. And that's the difference between a false alarm and a real-time rescue event, right? We hope that we get to the point to actually be able to track the movement of a landslide, for example, and that can be done, for example, if you located windows of the seismic data, and then you can see the movement. For now, we are happy if we get as precise and accurate as possible to either to the top or to the toe of such geomorphic event, which is constrained in terms of geographic area.
And just a quick follow-up. So this is all kind of post-factum analysis for search and rescue theoretically, but could you see the potential for this to predict such events or for early warning systems?
But for early warning systems, I would say I'm more optimistic. For prediction, we still need a lot to do. Prediction is extremely difficult to do. And I by no means pretend that we can predict right now. For early warning, this could be a good solution because it's a light, elegant, and simple algorithm. There's no machine learning, no training, no AI. It's not data hungry. You just put it on a simple device, and in real time data, it should be able to pick and to tell you where within 5 kilometers, hopefully at one point, tell you where it happened. Now about prediction, that's a little bit more, we need more information, more data and to think, but I think the bio inspiration is the pathway for prediction, and that's a personal opinion based on experience with working with these strategies.
I have a question for you, and then I'll come back to you. So what about climate variables? So landslides are influenced by the amount of precipitation, the intensity of it, and the slope, the topography, and so many factors, other factors influence it. So how do you see those meteorological variables impacting your algorithm or the detection?
The detection itself and the location is independent of climate variable in a sense. So the climate variables cause geomorphic events, so we will just use it more frequently and we can improve its precision as we use it and we get experience. The climate variables are not included in the detection process, so they are not direct. They are just indirectly impacting our landscape, and therefore we have more events and we can apply it more often. Now, in the question of prediction, climate variables will play a crucial role. They will be the key component in trying to actually forecast, but that's a very ambitious plan to do. In that case, I think because most of the landslides and most of the geomorphic events are climate driven. So this is why the direct link between the two, this driver and the geomorphic events, is so important. And to actually, my algorithm will help quantify this link. And by understanding, putting numbers on this relationship, then we have a better understanding. So indirectly, climate variables are very important. But like how my algorithm is going from vague information to more precise one, that's a bit independent, mathematically.
Hi, sorry, one more on just to follow up on that on the landslides, because landslides are very difficult to they're very difficult to detect and locate as you are working at. But just to quantify the sheer number and the impact of climate change on them and around the world, one person I know does it by fatal landslides, and he maps and counts the number of fatalities caused by landslides around the world every year, and obviously it's going up. Do you think your technique could be applied to enhance the available data on the sheer number of landslides around the world?
Yes, exactly. That's one of the advantages of this method. Where satellite data is unavailable or not relevant to actually see geomorphic events, or where there are no witnesses, this method, if we have seismic stations like within even hundreds of kilometers, but we need seismic stations and we have this data, and the data is not corrupt or of poor quality, then we can pinpoint events that we otherwise couldn't see. So we can have numbers and hidden processes basically revealed through this process.
You could advertise yourself, really.
All right. Do we have any other questions?
Which is anyone going to start using this?
I hope so. I really hope so. So the next step would be to publish and to make the code with no parameters needed to be tuned by users. So it will be very simple and easy to use. And I hope that many people will use it, because the more information I get, so the more data is applied on, the more we can understand if it actually works, and we can ever make it better, or to have, as the question before pointed out, more numbers on geomorphic events and how to move to prediction.
Hi. Interesting work. The climate extremes and power grids. So I have a question for you. So when you looked at the data, did you get to see which extremes were impacting more on the power grid? Was it hot extremes or cold extremes or any other climate events? And the second thing, if I understood correctly, you mentioned it was very hard to pinpoint where the power outage actually occurs. So why is that?
I would assume by the reports, they're made by distribution system operators. They're provided by them. And they have certain categories where they put in when the fault happened, they need to investigate and so on. And there are a few categories within weather domain. Most of them are due to lightning strikes. Tree falls due to wind, tree falls due to snow, rain. So there are a few categories. They don't look really at heat or cold in that sense. And that's where I come in, where I look at the meteorological data and try to combine. So they're very, I don't know which word to use, but limited in the sense of explaining what actually happened. You can also pinpoint in the sense, you can see what voltage level was it, what company was in charge of that part of the grid, but you cannot see exactly where it happened. So it can be a region within Sweden. Yeah.
So in your opinion, if they have to make changes to their power grid based on the climate extremes, what changes do they have to make?
So they need to anticipate these events for like to predict scenarios that could happen, that could impact. The problem is these extreme events, they're very high, low probability of occurrence, but high effect. So it's very hard to predict them in that sense. So everybody how to like anticipate, adapt, and prepare for future.
Yeah.
Yeah. Do we have any further questions? Nope.
Hi, Heba, that was a really interesting talk. So one question is that you mentioned about these different green techniques that are available. What are the costs associated with adapting to these green techniques? Do common people, when they adapt, what is the cost associated with them? Like they would want to go for a cheaper house because houses are anyway so expensive. So what are the costs associated with trying to adapt to green?
Thank you. Yes, this is very important question because the cost is very important. Based on that, when we started this project, we select type of house or type of residential building, which is considered as a moderated cost, not high or not low. But it is not green building, it is ordinary building without any certificate. So we consider the cost, but some increasing of the cost coming, but not too much from the first stage. But during the building lifetime, this is cost, if we consider this cost, it will be not too much. In the same point, green concrete, when based on recycled material, and this is recycled material available in the local market, and also have opportunity to increase the labor training for using this material, so there is a labor cost is not too much. All of these factors can make it the green concrete availability is better than before. Day by day, it will be increase the awareness for ordinary people to using this material, and how can this is have benefits from cost and from other environmental impact. But now in regarding some techniques like system dynamic and like stock and flow diagram techniques need for more specialists and more technician have more experience for predicting what is the risk assessment can be faces this strategy in the future. So the selection for the case study is very important, coming from residential, not commercial, because residential can be have a resilience for how can make the variety for this for this type of concrete. We use a different concrete type. Some type of concrete is very expensive. We don't use in the residential building. We consider this is reduce the costs, but the most one cost effective, which included several type like fly ash, recycle aggregate, and depend on the construction and the demolition waste. And also there is one point we focus on, recycle on the site, because the site, when we start construction processes, we find that the recycle for the construction waste on site can reduce the cost for transportation. So it is coming the cost maybe little low. For this reason, we consider all of these aspects when we select the case study. Maybe in the other building typology coming very high regarding the requirement for building load and the structure and so on. But for low-rise residential building in this same area, urban area, it is considered as a low cost, not too much high. Thank you so much.
Thank you. Any other questions? Well, thank you again so much for our brilliant speakers. Let's give them all one final round of applause. And thank you also for our attendees. So I want to tell you that this afternoon at 2 p.m. we have our 5th press conference run-in, 2 p.m. Berlin time. And it's titled From Soil to Supper, Plastics in Your Fields, Waters and Lungs. So make sure to tune in. Thank you.